This is another example of projectile motion problem. But before we get to the problem, we need to do a little cool factoid. In the world of Dr. Seuss physics, where there's no friction, no air resistance, and all energy is conserved, etc., after bouncing off a wall, the two projectile paths are mirror images of each other. So let me show you what I mean. Here's a ball, it bounces up, hits the wall, bounces off, but you can see if it continued through the wall, it would follow the same path, just that when it bounces off the wall, it's a mirror image of that. That's going to come in handy on this example problem. Let's do a quick solution overview. So these are the steps you would follow. Now, I wouldn't expect anyone to write these down, but it's good when you're starting to at least understand where you're going and what you're trying to do. So the first step is to break up the initial velocity into vertical and horizontal components. What we're going to do is create a triangle of vectors to do this. Second, we're going to identify the positive directions using the initial velocity as the direction of the positive numbers. So vectors that point in the same direction of the initial velocity will have the same sign. Vectors that point in the opposite direction are given the opposite sign, because for us, signs indicate direction. We're going to fill out this givens table, and that's going to be a way of organizing ourselves. And we're going to calculate, in this case, the time by using either vertical givens or horizontal givens, both, and we're going to use kinematics equations to do this. Now, you don't always have to find the time, but for what we're doing, it's going to work. And then we'll use that answer in other kinematics equations to answer the question. And these are the basic kinematics equations that you should have memorized by now. When we do our problems, the initial position, we're always going to assume that it's 0 no matter how high you start or how low you start. So that means that x naught for us is always going to be 0, and that's going to make the math a little bit easier. So here's the problem. A ball bounces up off the floor at 10 meters per second while making an angle of 50 degrees with the floor. It hits the wall 1 meter up from the floor. How far away from the wall was the ball bounced? In other words, I'm looking for the range. So let me kind of take this down step by step. Before we get into the details of the problem, let's do a couple things. Let's start by drawing the range on the picture, that was mentioned in the problem, and we'll draw the other distance on the picture. So the range is from where the object becomes a projectile to the end of the problem, so that's the horizontal distance over, that's the range right there. And it says 1 meter up when it hits, so 1 meter up on the way up. Next, we're going to draw a vector that's initial velocity. You want to make it at least 2 inches long. We're going to turn this into a triangle of vectors, and we need long sides so we can show the math next to each side all around the triangle. So here's the vector, and I'm going to draw it on the diagram as well, just so I have some kind of reference as to what I'm talking about. And that's V naught, 10 meters per second, and 50 degrees with the floor, so that's going to be 50 degrees with that horizontal line that's drawn there. Now I'm going to make my triangle of vectors. Remember, you start at the tail, go over, connect them tip to tail, and then go up to where the two heads meet. So these are the components of the initial velocity. Once I figured out how to calculate these components, I'm going to ignore the hypotenuse of 10 meters per second and the 50 degrees, but only after I do the components lengths. So that's my next thing. I'm going to write a trig equation that can be used to calculate the horizontal and vertical components. So for this, it's 50 degrees. The opposite side is going to be using the sine function, and the adjacent side to 50 is going to be using cosine. So it's going to be hypotenuse cosine for the adjacent, hypotenuse sine for the vertical. Now in projectile motion, it's not always true that cosine's horizontal and sine's 50. It's just in this case. If you always use trig to figure this out, you will always get the right answer. Okay, now we're going to draw a givens table. And so we're going to use this Vox TVA notation. Alright, so let's look at the table first. So here's the table. And you can see how I really have 2 columns on it. One for all the givens that are up and down, the verticals, and one for all the givens that are left and right, the horizontal values. And the Vox TVA, this came up from a couple of students of mine a couple of decades ago. In order to memorize all the variables, they came up with the phrase Vox, TV, and A. And you can see vertically how it all fits, VOX, T, V, and A. So it's simple, it seems to work, it's easy to remember, so we'll stick with that. We have 2 columns because every time we have an acceleration, we have a column of givens. And I have 2 accelerations in this problem. I have gravity vertically, and horizontally I have no acceleration at all. So 2 accelerations, 2 columns of givens. That's why I have it set up like this. Next step, let's determine the signs, and we're going to do that using arrows. So our arrows are going to help us. The first arrow I'm going to draw is the direction of the vertical component of the initial velocity. So look at my triangle on the left. I can see I got 10 meters per second sine 50, and that points up. So that's the vertical velocity, and that's the positive direction. If the vertical velocity aimed downwards, so if something was thrown down, I would draw my arrow down, and that would be the new positive direction. So positive isn't always up, it's whatever direction the initial vertical velocity points. Now let's look at the distance. The distance x in the vertical direction is 1 meter and it goes up. So I'm going to draw a little arrow that goes up. T is a scalar, doesn't have direction, so I'm not going to worry about that. Final velocity is not in this problem, so I'm not dealing with that. And the acceleration, that's due to gravity vertically, and gravity always goes down. If it didn't, we'd have a lot of fun playing on the wall, but it always goes down. Okay, now let's look at some values and some signs. 10 meters per second, sine 50. Notice I'm not doing a calculation, I'm actually writing the equation, and there is purpose and value to doing this, so do it like this. And that's going up, so it's going to be a positive sign. X goes the same direction, so it has the same sign as V naught. Simple rule, right? 1 meter. The next one, acceleration is 9.80 meters per second squared. It's pointing down. Since it points the opposite direction, it's going to have the opposite sign. So it'll be a negative value. Horizontally, it doesn't matter if it goes left or right. Doesn't matter to us at all. We're going to make all the values positive. So that's going to make the math easy. And the acceleration is 0 horizontally, so that's easy. What's nice about this table is gravity is always 9.8, and horizontally the acceleration is always 0. So you know you have those two givens. Next, now we're really going to start looking at the actual question. All we've done so far is set up everything, and we're going to solve this with kinematics. So let me clear the screen a little bit, move some things around. Now I've got some space. All right, that's great. So I'm looking for the range. That's going to be this value in that spot of the data table. And to do that, I need another given in the horizontal column. And that given I'm looking for is time. The beauty about time is it's a scalar, so if I find it using horizontal givens, I can copy the value in the vertical column. If I find it with vertical givens, I can copy the value over in the horizontal column. So I'm going to find it with the vertical givens because I have 3 variables in the vertical column, and I know if in kinematics, if I have 3, I can always find a 4th. So I'm going to tell the user, in this case you, what I'm going to do with the math. So I wrote a little sentence here, or a statement actually. Find t using vertical givens, so you know what I'm doing with the math in case I do something wrong. And now I need an equation that'll solve this, and that's pretty easy to find. That's going to be x equals x naught plus v naught t plus 1 f a t squared. So I'll put in my givens. So 1 meter equals 0 plus 10 meters per second sine 50 times t plus 1/2 negative 9.8 meters per second squared times t squared. And remember, signs all came from the table. And then I'll put this in a standard form, so I'll set everything equal to 0. And notice I didn't calculate what 10 sine 50 actually is. I'm going to leave that out for a moment. Now to solve this, there are a couple ways. Your calculator actually does this if you have a TI-84. You can use PLY-SMLT2 app on your 84. Or, there's no reason why you can't just pull up Google and search online quadratic equation solver. There are lots of them. I think the first one that comes up is from math.com, so that'll work just fine for us. Put in the numbers for A, B, and C from the standard form. If you don't know how to do that, you might have to do a little bit of thinking, a little bit of work on that. And they'll give you 2 values. So I get 0.14 or I get 1.42. Well, they're both positive, so I can't just say, well, time can't be, negative, for example, if you get a positive and negative answer. So now what do I do? So at this point, you got to kind of get away from the math and start looking at the problem for some other kind of clues. And here's the clue that involves the factoid. If I draw a line on the wall, and it line's long enough, you can see that my projectile, when it bounces off the wall, it crosses that line twice. Now remember, if the wall wasn't there, it would still cross the line twice, just on the other side of the wall. So both these times are valid. But now I've got to figure out which one of these times is the one that I'm after. And if you look at the picture, you can see that I'm after the one for the ball on the way up, because on the way up is when it hit the wall, not on the way down. So I want the shorter of the 2 times. So I'm going to use the 0.14 time. And I'll write it in both columns just as a reference. It doesn't really have to be there, but that's just me putting there for a reference. Now I'll tell the user what I'm trying to do, so I'll write a little statement, find the range using the horizontal givens. I'll use my range equation, which actually comes from this long equation, x equals x naught plus v naught t plus 1 f a t squared. I'll get rid of everything that goes to 0, that's the acceleration, and x naught, leaves me x equals v naught t. And that we use so often, we're just going to call that the range equation. So range is equal to the horizontal initial velocity times the time. Put in my values for the range, 10 meters per second cosine 50 times my time 0.14 with all those decimals that you see, and I get a range of 1.10 meters. So the ball hit the wall when it was, the ball was 1.10 meters away from the wall when it bounced off the floor. And when I solve it on paper, this is what my paper looks like. You can see how it reads from left to right, and it goes in kind of rows as I go across. So it's easy to follow. It even has the expression of what I'm trying to do with the math. And I didn't squish everything together. I left lots of space. Space is your friend when you're trying to convey what's going on in the math world.